Welcome back. Today we are going to carry on with our introductory material, and we are going to talk about the second law of thermodynamics. Specifically, we're going to start off with historical statements of how we can express the second law. So back in 1854, so you can see that with the second law, we're very, very much more so into the future than we were with our first law discussion. We start off with a name that hopefully we should all recognize from thermodynamics in the past is Clausius. His statement, and I'll draw it out schematically, is that you can have no process by which heat is being transferred from a cold body to a hot body without putting work into the process. So if this Tc is the cold temperature, Th is a hot temperature, this would be heat being transferred. This is not possible. And just to be clear, in this case, Th is greater than Tc, right? So Clausius basically said that one way to formulate the second law is that heat cannot go from a cold body to a hot body. But we'll notice that in this definition, we rely on the concept of temperature, we rely on the concept of heat. Another formulation of the second law is by Kelvin in 1851 and by Planck in 1897. And it basically says that heat, let's see, I'll say it out and then I'll sort of paraphrase it because it's a long statement. No process is possible, the sole result of which is that a body is cooled and work done. So what that means is that you cannot directly convert heat to work. That is sort of the essence of the statement. So what that means is that if I have a body here at some temperature, I have some magical system process, we don't care what it is, I cannot put heat into the process and expect only work to leave. So this again is not possible. So if you recall from the Carnot cycle derivation, this is close to what the Carnot cycle looks like, except you have a heat rejection part of the cycle. Again, this definition of the second law relies on the concept of temperature, heat, and work. So it is not necessarily the most elegant formulation of what we can accomplish here. Now, the biggest leap in the definition of the second law is in 1909 by a mathematician, Carathéodory, C-A-R-A. Now, this one was sort of the first mathematical framework of the second law. But for our purposes of engineers, it seems sort of overly pedantic. But in the case of a mathematical proof, where you're defining a set of axioms, you're defining a set of properties of the mathematical structure of entropy, it became exceptionally valuable. Right? So for example, the concavity of entropy is sort of formulated by taking a more strictly mathematical approach. So this was called the self-evident mathematical foundation of thermodynamics. And I will read out sort of the concluding statement, and then I'll paraphrase it. In any neighborhood of any state, there are states that cannot be reached by an adiabatic process. Right, not necessarily something to write home about in terms of its impact. So what we're saying here is that basically, in fancy mathematics, systems cannot spontaneously go to a state with lower entropy. It does seem a little bit like cyclic logic at this point, but in terms of mathematicians, this is where we were able to define a lot of the mathematical properties of entropy itself. But as we noted, right, this is the first definition that doesn't rely on other properties. Right? So really, by saying that you're defining the second law based on how it interacts with the physical world, you're really putting the cart before the horse, in a sense that temperature is defined based on how entropy behaves, but you can't, so you're kind of then chasing your tail. So this one here is really the first formulation. And in years past, I had actually covered a different definition of the second law from 1999. A physicist and a mathematician, I believe, from Princeton, wrote like a 50, 60-page article redefining the second law and highlighting only the most essential axioms required to formulate it in its modern form. So 1999, right? So we're still tinkering away with the second law of thermodynamics. Okay. At this point, I'd like to bring us into the modern era very, very quickly. So my key question is, when we started off, we basically said that the second law of thermodynamics can be written quite trivially like this. Now, in your homework assignments, when you were an undergraduate student, I'm assuming you didn't start every problem with this term right here. So instead, most everyone probably started with an expression that looks very similar to this here. The rate of change of entropy as a function of time. So one quick note on the notation. In thermodynamic math, right, we typically don't put the denominator of these integrals or these differential expressions, because as they're state functions, we don't really care how we get there. So we just know that if I'm going to change the entropy, I'm going to be changing something. The temperature, the pressure, the internal energy, the density, time is going to elapse. It doesn't really matter what we choose. So these relationships hold true regardless of what the independent variable is. That's why we skip over that. But from a practical engineering perspective, right, we're looking at an unsteady state entropy balance. So the rate of change of entropy with respect to time is the heat input plus the rate of entropy generation. This is probably the starting point for most everyone's entropy balances. Now, if it's an open system, entropy is what we call extensive. So the more fluid that you have, the more entropy exists. So you can add in, for an open system here, for example, plus the summation of the molar flow rate of every species and the entropy of the species either going into or out of the system in terms of flow rates. Right, this would be for an open system, but for here, we're going to be re-deriving our discussion on a closed system. Okay, so the question is, how do we go from this concept to the expression that we all use? And I've never seen this really done in a lot of books, so I like to go through and do it. What we will do is we will build a universe and perform balances on it. Okay, so I have a system contained within an infinite bath. This system has a given temperature, it has a given volume, and it has a given internal energy. The volume is going to be constant, which allows us to neglect any work in the form of pressure volume expansion. Just simplifies our expression a little bit. Outside, the bath is infinite in size, meaning any energy that transfers into or out of the system is going to be negligible. In my balance, to make things work out, I will define heat as positive going into the system. It just makes it so that this expression looks the way that it does. And let's see. So this bath and it's infinite. Infinite bath. Okay. So how are we going to derive this? Is we are going to start off with our second law of thermodynamics. Property number one of entropy that must be considered to progress is that it is extensive. Extensivity basically means that we can add and subtract entropy. So in this case here, ds is equal to the rate of change of entropy of the system plus the rate of change of entropy of the surroundings, and it must be greater than or equal to 0. So we'll take a step back and we will do the energy balance also. And then basically combining the energy balance and the entropy balance should get us to our objective. Okay, the total change in energy of the system is going to be 0 if we assume that this is isolated. That's all saying here, isolated. The other way we can think about this is the law of conservation of energy stipulates that the total energy of the universe has to be constant. So the rate of change in the energy of the universe has to be constant as well. This corresponds to the change in internal energy of the system. And you add the change of the internal energy of the surroundings, that corresponds to nothing happening, such that the energy gained by the system is equal to the energy lost by the surroundings. So this is first law on the universe, we'll say. If we do the first law on the system, the change in internal energy of the system is equal to the heat going into the system plus the work going into or out of the system, which we are calling that 0. Now, we need to link our energy balance and our entropy balance together. In order to get this particular form here, we are introducing a new concept and a new variable, which is the temperature. So we will actually be relying on the definition of temperature to even develop that equation right there. So temperature is defined as the rate of change of entropy with respect to the rate of change in internal energy. So if we rearrange this, we can see that the rate of change of the entropy of the system right? We just rearrange the definition of the temperature of the system. If we substitute in our energy balance, we can then write this as the heat input over the temperature. Likewise, we can do exactly the same thing for the surroundings. In this case, it'll be minus Q over T. We insert in our second law of thermodynamics, noting that we are taking advantage of the mathematical property of entropy that is extensive. This is what we want. We want to know how does the entropy of the system change, which will be ultimately that expression there. So the entropy of the system change is equal to greater than or equal to minus ds surroundings. I substitute in my definition of the temperature, and we see that ds is greater than or equal to q dot over t. Or we can also write ds is equal to q dot over T, the heat input over the temperature, plus some additional term where we say that the entropy generation has to be greater than or equal to 0. Right, so we get rid of the inequality by adding in a term that has to be positive, which personally I think this is a lot nicer to work with. Inequalities have a little bit of nuances that are just not necessarily worth taking the time. So this expression here, we now know, is really just an expression of the temperature and what the temperature means. Because we really haven't done anything fancy except for really defining the direction that we're calling positive heat work. We're saying work is positive going into the system, which is just a convention. In real world balances, it doesn't really matter. Right? Well, this expression could just as easily have been a minus Q if we defined heat going out of the system. Nothing matters. I mean, there's a huge debate among authors of undergraduate thermodynamic textbooks of whether or not work should be positive going into or out of the system. And I will state here, for everyone to hear, I don't care. Just give me a drawing and then draw an arrow going into the system, or give me an arrow drawing out of the system. Because when you have a complex balance with multiple processes, you have to define a positive direction for heat and work at some point, right? So it's only a pedantic argument for a simplified, really small system. So positive and negative, I don't really care. So in any exam or quiz or homework, all I ask is you just say, give me a number, and then say whether it's going into or out of the system. That's all I care about. The final answer, this amount of heat going in, this amount of heat going out. Any questions? I've always enjoyed doing this derivation because I had never seen it done, so I sort of took the time to work through a flow that made sense to me. But again, it highlights, I think, the utility of treating entropy from a mathematical perspective and not necessarily from a physical perspective. It allows us to sort of understand then that the concepts that we work with are really a commingling of the second law with arbitrary definitions already baked into even the most basic equations that we are working with. Now, again, with our first law, we wrote out the expression that we will use as the starting point for all of our homework problems and quiz problems. Yes, question?
Oh, yeah. How does gravity work with entropy? Does gravity increase entropy somehow?
So anything, and I think if we have time we'll get to it today, but anything that has a gradient will produce entropy. Now, how do we model the gradient of the gravitational field? I would say that yes, gravity must create entropy. So I'll do a demonstration here about a temperature difference as the way that entropy is generated. So this term right here, how is this physically generated? Basically, any gradient in any field produces a rate of entropy generation. I do not know how they actually model that with respect to gravity, but I would assume that that concept may apply throughout. And since gravity is a warping of the space-time, I would tend to think that that warping of the space-time produces a space-time gradient that should be generating entropy in the process. But I would be embarrassed to have a conversation with a physicist who knows what they're talking about on that subject. But very good question, thank you. So the starting point that we would like to use for our class that is actually practical is the open system entropy balance here. And just for the sake of discussion, I will write out our open system energy balance as well. Now I've added on a little bit here, but I don't think it's too much of a leap of logic to break it down into a couple of different forms. The rate of change of entropy of a system. Now a system is anything that you can draw a circle around, right? It doesn't have to be a perfect like object. You can be very fine and very careful, right? So I could basically magically draw a system around individual gas molecules if I wanted to, right? And then I could watch it expand and move and really track it. But basically anything that I can build a barrier around and keep track of what goes in and out, that's a system. The accumulation of entropy as a function of time is going to be the mismatch of the flow rates in and flow rates out. So if I have an accumulation of mass, I have an accumulation of entropy. If I have a difference between the flow in and flow out of the entropy, I can have accumulation of it. I also have this term here. Any heat being transferred into the system is going to contribute to the entropy, and I can also generate entropy on the inside of the system as well. Likewise, with the energy balance, I can have a mismatch of energy flowing in or out in the form of chemical bonds, kinetic energy of molecules. I can have heat coming in, I can have shaft work. This would be like an impeller stirring a tank, WS shaft work. I can also have the whole system expanding and contracting. That would be PV expansion work. It is negative because as my volume gets larger of my system has to push back the surroundings and it has to give away energy to those surroundings. This is your starting point for everything that we are going to do for the first week or so of the class. These two equations here are going to comprise the entirety of a first semester thermodynamics course. I'm not going to give basically any examples of how to use these equations because we've seen them all many times before, hopefully. And the equations are just relatively simple algebraic expressions. The challenge of thermodynamics is not in the energy balances and the entropy balances. The challenge in thermodynamics are estimating the internal energy as a function of temperature, pressure, or fluid density, and in the ability to estimate the entropy as a function of temperature, pressure, or density. Now, because we know the Gibbs phase rule, only two of these three variables have to be defined. But everything is a function of everything in thermodynamics. Conventionally, right, we like to think that U is related to T and V. That's really just more of a matter of convenience. And H is related to T and P, right? But at the end of the day, all thermodynamic variables are functions of all other thermodynamic variables. And so when we write a partial derivative, like ds du at constant v, this here is just a reminder to us of the system that we've established. It's not critical, right, because this is a partial derivative. In a partial derivative, every other variable is held constant, right? But because in thermodynamics, it matters which variables are being varied and which ones are being held constant, because that changes how we construct the system of how we're performing our calculations. That's why we leave this little here as a notation to help us remember where we started and where we're going to go. So, if you have access to the steam tables in the back of any engineering textbook, I expect that everyone here can more or less apply these equations. to calculate the work generated by some turbine, the heat input associated with some PV compression of a gas, either in a closed system or an open system, the entropy generated in a heat exchanger, right? So one example that I will give as a homework problem, if I have a heat exchanger where energy is flowing from one fluid to another, and I'm asking you to tell me what is the rate of entropy generation. I'll go through in a moment here that entropy generation is related to temperature gradients. I would say about half the people in the class or more will try and use this term to solve that problem. I'm going to tell you here on out that this term is almost never useful. It's very useful in derivations, but in real practical problem solving, it is not useful at all. So in the example of a heat exchanger, one may want to do an entropy balance on fluid 1, calculate the heat out, and then somehow relate that to an entropy balance on fluid 2, keeping those heats constant. Now this could be an approximation approach to do so, but the problem is the temperature at which the heat is being exchanged between the two fluids is not constant. So if you wanted to apply this expression here, you would have to then develop some sort of a quantitative expression for how the heat changes and the temperature changes as a function of a volume element of fluid traveling through that heat exchanger. Right? So at one point here, right, the gradient is at a certain position. At one point here, the gradient is at a different position, which means that the rate of heat transfer is going to be different, which means the temperature is going to be different. Now that's a lot harder problem than what I recommend, is that you just do an entropy balance of the whole process. In which case there is no heat being exchanged, and the entropy generation is simply just the mismatch of the flow rates in and flow rates out. It's very, very simple. But I assure you that if I did not go over this, and even the fact that I did go over this, someone is going to try and apply this expression here. This expression only works when I have a nice, cute system like this, where I'm magically inserting my system into an infinite bath where the temperature is constant. That's the only time I can really ever use this. So just keep that in mind, burn it into your brains. So in terms of balances, if I give you a Rankine cycle, if I give you a Carnot cycle, if I give you an Otto cycle, if I give you a compressor, a turbine, anything, the only thing that you need to do is this expression here, go to your steam tables, and look up what the entropy and internal energy is of steam or any other fluid at a given temperature and pressure, plug the numbers in, and tell us what the heat is, tell us what the work is, so on and so forth. The challenge that we are going to be focusing on is in building the tables with predictions to estimate these properties. That's the real challenge. Okay. So let's see, where do I have this? Since I've been talking about it, let me just go ahead and do that entropy generation balance. Here we go. Lots of time. 10, 30, 20 minutes, okay. Sorry. Do a little math in my head. Again, the only way that I'm really going to be utilizing excuse me, that Q over T term is in playground, sort of cutesy little sandbox environments. So I build one of those systems. I have chamber A. I have chamber B. This system is completely isolated from the rest of the universe, such that the heat in and out of the system is 0, the work in and out of the system is 0. Nothing goes in, nothing goes out, it is a rigid wall. I'm going to define positive heat as going from the A chamber into the B chamber. So we have a barrier here. And what I'm going to say is that the Q dot, the rate of heat transfer, is very small. Now this could be if I have like a really thick styrofoam barrier or an insulating barrier between chambers A and chambers B. Now that assumption allows me to make a subsequent one, is that the temperature inside chamber A is homogeneous, meaning that there is no gradient inside chamber A, and that the temperature inside chamber B is homogeneous. Now in a real system, right, let's say for example there were to be a fire in the hallway. We would feel the heat here before we would feel it over there. That is a gradient in the temperature that we are trying to avoid. So by having the heat flux be very small, that means that internal sort of physics can homogenize the temperature on either side of the chamber such that it's two homogeneous temperature differences. And we will see why that is necessary in a moment. Okay, so if we do an A balance of the entropy, we have the rate of change in entropy of chamber A as a function of time is equal to, let's see, did I do this wrong? No, let's see. Oh, I think the way that I drew this here is actually, this is backwards. How did I fix this? All right, well, I believe I'm doing my balance this way, actually. Sorry. Looking at my math. Excuse me. Closed system, only heat is going in and out. Because there's no gradient on the inside, I'll tell you why this works, but for now, let's assume that there's no entropy being generated on the inside. The outcome of this derivation will demonstrate that that is the correct approach. I'm going to model the heat transfer coefficient, the heat rate transfer, by a heat transfer coefficient using the temperature difference between the two chambers So basically, the bigger the temperature difference, the faster the rate of heat transfer between the two chambers. Adding in a little bit of physics after the fact. Such that then I can write this energy balance, this entropy balance here as d as t. All right. So what we've done is just done the closed entropy balance. And I've written in an expression that makes physical intuitive sense. The bigger the temperature difference, the faster the rate of heat transfer between the two, and just substitute it in. If we do a balance on the B chamber, we get basically a very similar result. And I'll just do all the approximations here, the substitutions. So the only thing that matters is different is that the temperature of chamber B is different, and that we've changed the sign. So that basically means heat goes from one chamber into the other. Okay. So what we will then do is put it all together and do a total entropy balance of the whole process. So the total entropy of the entire system, so chambers A and B added together, is going to be equal to the total heat going in and out of the system plus some entropy generated. This term goes to 0 because it is an isolated system in the universe. Which means that the rate of entropy generation is going to be the addition of dSA dt plus dSB dt. Exactly like that heat exchanger example I demonstrated. So if we do our substitutions here for the two different relationships, we will get what we're going to do is do a cross multiply to get this to be combined. And what it'll end up being, I'm going to skip over the math. The final conclusion, I got to say, everyone a second to write down the formula.
Dr.
Yes.
Just a quick question. So for this body, you're considering the heat is flowing from B to A, right?
It's just a convention. At the end of the day, it shouldn't make a difference.
Okay.
It's just so that I can just keep track of which one is positive and which one is negative and things like that. But basically, if I switch the direction, one will be positive, one will be negative, and the outcome here will be exactly the same. It should be. Yes?
Is it okay to assume the entropy generation to be 0 for A and B, but not for the whole system?
So good question. So the question is, I'm going to try and remember to repeat it for the video. How can we assume that the entropy generation is 0 inside the individual chambers, but not for the universe? Not a good. So this is not a good mathematical evidence right now. But if we take the conclusion here that a temperature difference is the entropy generation, that gives us this assumption here that if we say the rate of heat transfer is small, then we can assume that the temperatures inside of each chamber is homogeneous. But you're right. Any gradient in any form will produce entropy generation, which goes back to the question over here about gravity. I believe if there is a gradient involved, entropy must be generated. But I do not know, but I know, and I know it's been done, right? Because thermodynamics has been sort of lumped into any sort of astrophysics problems, but that's something I don't know how it's done. Okay, a couple of notes. Anything that induces a gradient causes entropy to be generated. If we have a reversible process, reversible means not that entropy doesn't go up or doesn't go down. Reversible means that no entropy is generated. So let me write that out just so we're explicitly clear. When we say reversible, this means one and only thing. S gen is equal to 0. So I can compress a gas reversibly. That doesn't mean that the entropy of the gas doesn't change. It just means that I'm not generating any entropy when I compress the gas, right? If I say it's adiabatic, that means Q is equal to 0. If my heat is not going in and out of the system, if I'm not generating any entropy, then my entropy cannot change. So if I put reversible and adiabatic together, that means my entropy is constant. The rate of change of entropy is 0, or delta S of the process is equal to 0. But reversible, with this physical insight now, tells us that it's never possible to do something reversibly. If I wanted to design a heat exchanger that was reversible, it would be infinite in size, because I would have to ensure that fluids A and fluids B would only ever be in contact with one another when their temperatures were very, 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 very close together. And I could never design a system where there was a gradient that was tangible and finite. If I'm compressing a gas, that one's a little bit more easy because gas molecules respond to the pressure more quickly, right? But any gradient in pressure, right, water flowing through a garden hose, There's a gradient in pressure from the spigot to the outlet of the hose. That produces entropy. A gradient in composition that causes diffusion. That generates entropy. So there is no physically possible way to ever do a process reversibly unless you take an infinite amount of time to do so. But we will use that relationship because, as I mentioned before, I erased my balance here, but if I'm trying to predict what the entropy at some temperature and pressure is, or what the enthalpy at some temperature and pressure are, right? Same thing like with the mass example. A kilogram is a kilogram is a kilogram. Doesn't matter how I got there. Entropy only is going to depend on temperature and pressure for a pure fluid. Enthalpy is only going to depend on temperature and pressure for pure fluid. So if I'm going to design an arbitrary system by which I can calculate what is the enthalpy or what is the entropy, I'm going to do it reversibly. But when I try and build a real chemical process, I cannot do it reversibly. But because these are state functions, in math world, I can do it reversibly because I can take an infinite amount of time, because in math it doesn't matter. So that's going to be the disconnect between the balances of real world processes and the calculations that we're going to be spending most of our time on. Most of our time is going to be spent on estimating these from an equation of state. Because the balances part of it you've already covered. And it's relatively straightforward compared to the complexities involved here. And then in the future, we're going to then use this equation of state to do something like vapor-liquid equilibrium or liquid-liquid equilibrium, which is going to necessitate understanding the Gibbs energy or the Helmholtz energy, which are really just manipulations of these terms itself. So if we can predict what the enthalpy and entropy, or internal energy and entropy of a fluid is from an equation of state, we can do all of our phase equilibrium, and that's where chemical engineers make their money. No one else in the world does chemical separations like chemical engineers do. There isn't another discipline, other than maybe some chemistry, that would focus on, let's say, distillation. That's really chemical engineering's home territory. One last comment. The definition of temperature really contains a lot of physical insight with entropy. Let me write this out another way. So you'll notice in our balances here, in this expression, in the denominator, we have temperature A. In this expression here, we have temperature B. In a real-world system, the internal energy kind of always looks a bit like this. Whereas the rate of energy change gets really, really sort of steep. Actually, no, that's not. Let me think about this. No, I think this is, let me do the entropy rather, not the internal energy. Entropy has to look like this. And if we do entropy with respect to U, let's do this here. So if we look at this plot right here, then we know that this gradient here corresponds to the reciprocal of the temperature. As T goes to 0, 1 over T goes to infinity, which makes sense, right? As you get to absolute 0, or no energy in the system whatsoever, your rate of change of entropy gets to be infinite in slope. And this is effectively why you can never reach absolute 0, because you have to pull away so much entropy that your function diverges. This is also the source of why why gradients produce entropy. Based on our understanding of temperature from a thermodynamics perspective, 100 kilojoules of energy given to a fluid at one temperature doesn't change its entropy as much as 100 kilojoules of energy given to a fluid at a different temperature. So if I'm going to heat up some sort of a fluid, right, from absolute zero back to room temperature, if I give it some quantity of energy here, I'm going to induce a massive delta S of that fluid that's very cold. If I give the same amount of energy to a fluid that is at a warmer temperature, you'll see that my entropy increase is much, much smaller. And this is sort of one of the confusing parts about entropy, is that it's extensive, but it's not conserved. Right? You can generate entropy. The reasoning for that can be visualized in a number of different ways. But if you just note the fact that entropy is concave, and that temperature is defined based on how entropy is manipulated as a function of other variables, everything starts to fall in place a little bit. So that's going to be one of the key areas, sort of I think really useful physical insight. And these are sort of global concepts that apply in all circumstances. And so we don't have to worry about whether or not it's an ideal gas or not an ideal gas. We know that anything any model predicts must show these properties and these characteristics. All right. So the last little bit that we have here is I'm just going to go through and sort of demonstrate with our modern formulation in the last couple of minutes that we have. With our modern formulation of the second law, we're going to demonstrate that some of the systems that we talked about in the first, for example, Clausius's system, is wrong. So in Clausius's format of the second law, we had two bodies. One of them was cold, one of them was hot. We have some magical cycle that is then going to take the energy, oops, let me draw it this way. It's magically going to take the energy from one reservoir and reject it to the other. So what I'm going to do here is use this as an example of how we can perform entropy balances and energy balances. So what I'm going to say here is that I'm going to do an energy balance on this process, which is this little guy right here. We're going to say it's steady state. There is absolutely nothing wrong with this process from an energy balance perspective. All it is saying is that energy that enters this system from the cold reservoir has to leave from the hot reservoir. Leave to the hot reservoir. If we consider then an entropy balance, all right, we're going to assume that this magical device doesn't generate entropy either. So all we're doing is applying the closed form of the entropy balance because there's no mass flowing into or out of this particular process. So if we just simply rearrange this expression here, noting here that the QC is minus QH, what we can get then is that ds is equal to Q dot C. And I'm just going to hammer out a few lines of arithmetic here. Doesn't matter. Okay, just a few lines of arithmetic. So we could have done an alternative derivative where instead of saying that this is greater than or equal to 0, I could have left in S generation and then demonstrated that S gen would be less than 0 if these temperatures were switched. It's the same basic approach. But using the inequality, in this one I think it produces quite an elegant solution where it's very obvious that hot goes to cold and it is not possible to go the other way around, just borrowing the second law. So I'm going to reserve for a homework problem disproving the Kelvin and Planck version, where you basically remove heat and convert it 100% to work. Basically demonstrate that entropy will always be, entropy generation has to be less than 0 to occur that. And then also rederive the Carnot cycle, which can be done with exactly the same procedure that you see here, performing an energy balance and an entropy balance on a magic cycle. So just so you were aware, this is the Carnot cycle. And it actually doesn't matter which direction you draw your arrows, right? Because your math will all have to work out in the first place. But this is the Carnot cycle. That is not the Carnot cycle. Same with the Planck version was this one here. Right, where you have a reservoir going to some process and converting it to work. In fact, all you need to do is add in a second heat rejection reservoir for the process to work, and we can derive the Carnot cycle. Yes?
So you're proving Clausius right by showing that TH is greater than TC? I'm a little confused how
Sure, yes. So the Clausius statement was that no process is possible the sole result of which that heat is transferred from a cold body to a hot one. What this is saying here is that TC could never transfer heat to TH. So that if I have a system like this, let me get rid of my add-on here, right? If I have this system, it is not possible to have heat go this way because TH must be hotter than TC. I think if we had gone through and done the entropy generation approach, it would have been more clear. And let me see if I have the end result. If I have the end result that I can demonstrate for you. So if instead of this formulation here, we had done plus S dot gen equals 0, right? We removed the inequality. We could then solve for S gen, in which case S gen would be equal to, let's see, so if I do all this substitution here, let me just insert myself right here actually. Yes, so then I can, I'm trying to derive the expression here because my notes don't have it fully fleshed out, and I think the way that would highlight it. Okay, so if I do that, I manipulate this here. See, the problem is the cross multiplying divide. I'm struggling to do it right now off the top of my head without working through every step on the arithmetic. But effectively, S gen, and I wish I had the full algebraic expression for you, but S gen, the end result will be if TC is greater than TH, the rate of entropy generation will be less than equal to 0. I don't have the algebraic steps to get there, but that's something I can certainly put together, or I can make a homework assignment on. But the end result would be that the way that Clausius has defined the system, it is only possible for the net heat to go this way. Otherwise, you have to have a negative rate of entropy generation. But I do see that there's a disconnect, that it doesn't necessarily explicitly prove this wrong. It just says that TH must be greater than TC for there to be a net heat flow. But I do recognize that disconnect from a mathematical framework.
Sorry, I just have a question. Were we proving Clausius right or wrong?
His expression is fine. The
Okay.
way that he describes it is fine, yes.
Okay.
So yeah, so
I
Clausius understood the second law. And so the way that he defined the system, heat can only flow from hot to cold, is correct. And using our modern form of the second law, that is the truth.
Okay,
He
so we're
only
not
goes from hot to cold.
in the homework, we won't be disproving Kelvin and Planck, we'll be proving them?
Sorry, yeah. So you will
Okay.
be proving that their statements of the second law of bad systems that cannot exist are correct statements.
Okay, and that's what we do with Clausius as well.
Correct, yes.
Okay.
So
Sorry,
the way
I guess
that
I thought
Clausius
you were
formulated the second law, we demonstrated that the system that he described is impossible.
Okay.
Yeah, oh, I heard that too.
Yeah. and
Yeah,
so
yeah,
I was
yeah.
Flip-flop, sorry.
I think we threw in like 3 negatives on that expression. But yeah. So you'll be showing that they understood the second law correctly.
Just with bad systems.
Well, not bad systems. They're good systems for intuition, but they're sort of not super helpful systems for more complicated scenarios that entropy comes up in.
Okay,
All right.
that makes better sense.
All right. So have a good weekend, and we will come back talking about the mathematics of thermodynamics next week.